In this video, we're going to talk about limits at infinity. So last video, we looked at limits that were infinite. Here, we're looking at infinity. So we're looking at horizontal asymptotes, and it's very similar to a vertical asymptote. The definition says if we're looking at limits at positive or negative infinity, if we get a number, it's a horizontal asymptote. Most functions, as we look way off in the distance, their limits are infinity or negative infinity. So if it's a number, that means it's a horizontal asymptote. Otherwise, it's always getting bigger, always getting forever or smaller. A function can cross a horizontal asymptote and still be a function. It cannot cross a vertical asymptote because of the vertical line test. So this is kind of hard to maybe understand, but this is a theorem. We're going to look at R being a positive rational number. C is just a number. So anytime we have a number and we try direct substitution here, this results in a number split up into an infinite amount of pieces. So think of like a pizza to understand this. If I took one pizza and split it up into two pieces, those pieces got smaller. If I took that same pizza and split it up into even more pieces, each piece got smaller. If I split it up into even more pieces, every piece is getting smaller and smaller and smaller and smaller. So imagine I could take that one pizza and divide it into an infinite amount of pieces. Every single piece is so small, it's approaching almost nothing. So when we have a number divided by infinity, we call it equal to 0. Again, we're not saying the fraction's equal to 0, the limit is equal to 0. That means it's going towards 0. So, if we try an example here, if we think of this as direct substitution, we can plug it into this expression. We'll get 5 minus 2 all over infinity. Well, remember, this guy's getting so small, it's approaching 0. So this is really like 5 minus 0, or 5. Indeterminate form, another way to look at this is infinity over infinity. If this happens, another way to do this, because we're dealing with infinity, is to divide both the top and the bottom by the highest power of x in the bottom. Okay? When we look at a fraction, the bottom is always what causes problems. We don't like the bottom. And in this case, we're plugging in infinity. So we're going to get infinity here, and we don't want that. We want to get rid of that. Well, a way to get rid of a variable is to divide it by itself. If I do that in the bottom, I must also do that in the top, and that results in dividing every term by whatever we've chosen here. So this is essentially like saying 2x divided by x, and then here we'll say negative 1 divided by x. We're going to do the same thing in the denominator here. We'll take x divided by x, and then we'll take 1 divided by x. And writing it in this form helps us because now we can apply the last theorem. If we plug in infinity, each of these are going to go towards 0. So this is left with infinity minus 0 all over 1 plus 0, or infinity over 1, which is just so big it's still infinity. You may have remembered the 3 rules from last year. The 3 rules only work if we're approaching infinity. If we say the function does not exist, we still need to determine whether it goes to positive or negative infinity. I do not like the 3 rules because I do not like memorizing things. I would rather work through them mathematically so that I don't mess them up. If you want to, you can. So if we were to use the 3 rules on number 1, the degree of the numerator is smaller than the degree of the denominator. So we would look at rule number 1 here, and we know our limit is 0. So it can save you time as long as you don't mess it up. If, however, we were to do, let's say, the next example using our division technique, we know that this is the problem. So we want to get rid of that. We get rid of them by dividing it by itself. So I'm going to divide everything by x. In the numerator, I'll get 2x minus 3 plus 5 divided by x. In the denominator, here I'll get 1 minus 2 divided by x. And the reason I like this is even if you choose the wrong thing, it's still mathematically equivalent. So there's no messing up. If we try our direct substitution now, we'll plug in infinity for all these x's. I know that a number divided by infinity approaches 0. So in the numerator, I have infinity minus 3, which is still huge. In the denominator, I have 1 minus 0. So here's our summary. Again, we always try direct substitution first. So our very first thought, if that doesn't work, or let's say maybe we get one of our indeterminate forms, then we need to go further. So if we have to go further, we try to factor. Another technique that we didn't practice a lot was multiplying by the conjugate. If we have a graph or a table, we can use that. If the limit is approaching infinity, we can use our 3 rules. We can use our division technique. And this rule we'll learn after we learn derivatives. So we'll learn that rule in the future. If none of the above works, then it is possible the limit does not exist.